Oh, welcome to the fifth of the 7 lectures on the clay millennium problems. I'm glad to see that this beautiful spring weather has not won out against the attractions of these talks. It's probably unnecessary to explain again, but that these problems are unsolved. The lectures are intended to give you an idea of the nature of a few of the especially important unsolved problems in mathematics, what they're about. They are not reports on the solutions of the problems, as someone seemed to think last time. The solutions will require new ideas, new approaches, and I think I said before, the first lecture, to get $1 million, this is probably one of the most difficult ways to get $1 million to solve one of these problems. Anyway, our speaker tonight is Louis Cafarelli. He was born in Buenos Aires, is of Italian descent with a dash of Greek thrown in. He did his undergraduate and graduate work at the University of Buenos Aires. But after his PhD, he went to the University of Minnesota as a postdoc. And 6 years later, he was a full professor there. It was at Minnesota that he began working in partial differential equations, which is became his main mathematical love and the area of most of his research. He also fell in love with and married a student in Minnesota, also from Argentina, Irene Gamba. She is now a professor here at UT in mathematics. After his Minnesota years and before coming here, Cafarelli spent time as professor at the Courant Institute at NYU, the University of Chicago, and the Institute for Advanced Study. Since 1997, he's been a professor and Sid Richardson Regents shareholder here at UT. If I list all his honors, we'll never get to the lecture. He's a member of the U.S. National Academy of Science and a foreign member of several countries, several other countries. His work has earned him several prizes and medals, including the Boucher Prize of the American Mathematical Society. He has an honorary doctorate from the University of Madrid. He's author or co-author of over 160 research papers. In his spare time, he likes to play piano and is a serious chef. During his Chicago years, I'm told it was said that the best restaurant in the city was Chez Cafarelli. But to get on toward the lecture, one of those 160-odd papers was written 20 years ago by Cafarelli, Kuhn, and Nierenberg. Here's the review of it. Its title is Partial Regularity of Suitable Weak Solutions of the Navier-Stokes Equations. And I understand that that's of course a progress toward a solution of tonight's problem. And I'm told that in the last 20 years, in spite of the importance of the problem, there has been essentially no more progress. So, but let's let Professor Cafarelli tell us about the problem.
Okay. The problem with beautiful introduction is then you talk and mess it up. So but okay, well, it's a pleasure to be here tonight. And so let me start by writing what the Navier-Stokes equation is. It's a simple mathematical model to describe the way an incompressible viscous fluid flows. And There? Okay. So what I thought tonight, what I'm going to do is I want to first give you an idea of what does it mean, a mathematical model of a physical phenomena. Then describe a little bit what each term in the Navier-Stokes equation means. And finally, sort of discuss what are the difficulties of the problem. Okay? So, the matter of modeling the surrounding world is something that comes from the beginning of mankind. I think, the movement of the planets, the trajectory of a projectile, the hydrology, rivers and bridges and so on. People have been trying to sort of understand and predict the dynamics of the world around them. And through the years, they slowly develop a series of laws and methods. I was recently seeing once more the Leonardo Codex, that Lexington Codex that 5 or 6 years ago was bought by Bill Gates, and that the American Museum of Natural History had a beautiful presentation in New York when we were there. And there, Leonardo studies the flow of water and basically sort of says the principal relations, what is viscosity, what is pressure, what is capillarity. So the ideas have been there for many years, but it was not until the development of Newtonian mechanics that those concepts that people were able to write those concepts into mathematical formulation, into mathematical modeling. So the Navier-Stokes equation was precisely written by Navier and Stokes. Here is a picture of Navier, and this is Stokes. It really was written by Navier. Navier was a French hydrologist. I think the Napoleonic schools had a big influence in the development of fluid dynamics and many continuum mechanics in general. Navier was a hydrologist, was well known at his time for the design of bridges and channels and so on, and was just sort of a little bit of a side work for him to write the Navier-Stokes equation, and he wrote it in very heuristic grounds, but wrote the correct equations. And so about 50 years later, Stokes wrote it in the context of a full theory of fluid dynamics. So let me discuss a bit what is the nature of a mathematical model. So most of you know many simple mathematical models. Probably the simple ones is the fact that if you throw a stone, the trajectory of the stone is, at first approximation, a parabola. And therefore, you may predict the trajectory if you know the initial position and velocity. In other words, this sort of model you attain by reconstructing velocity and position, right, out of the simple law that acceleration due to gravity is constant downwards. And then from there, you write you can reconstruct the position. Of course, this is a very simple model, and if you want to write a more accurate one, then you have to take into consideration wind speed, the shape of the rock, the initial spin that you give to the rock, and so on. So in reality, given a physical phenomenon, there is a full family of models or different sets of equations that we can write to describe the same phenomena at different levels of complexity. For instance, in baseball, right, the parabola model is probably reasonably good for the outfielder that throws the ball far away to send it back to the pitcher. So he basically points up, throws the ball, and the ball makes a parabola, and the pitcher receives it. But if you want to reproduce a sophisticated pitch, then that's no parabola, right? That has a lot of spin, the wind enters into consideration, and so on. But such a mathematical model independently of how accurate reflects reality, it has to have some internal consistency. For instance, again, in the parabola model, you can prescribe the initial position and initial velocity with which the outfielder throws the ball, or instead you can, prescribing initial velocity, you can prescribe 2 points, the initial position and the points where you want the parabola to go through, which is really what the outfielder does. I mean, he sort of solves the inverse problem in his mind and throws the ball in the right direction, but he's solving the problem of where he wants the parabola to go. And this is another acceptable mathematical model. But if you try to prescribe velocity and the point where the trajectory goes through, most of the time you are overdetermining the problem and you won't be able to solve it. Okay? Or if initially, instead of giving the full velocity vector, you just give the speed, the ball can go in any direction. Nobody knows where it will go. So the problem in that case is undetermined. So there is this minimum self-consistent requirement for a model, which is to be able to sort of within some reasonable set of data to find unique solutions to the equation. Okay? In other words, you want to say, if you give me this data, then I can tell you that the problem will evolve this way. Okay? That makes, so this is self-consistent. It has nothing to do, well, it has some to do with the heuristic of reality, but it has nothing to do with the model really representing an aspect or another of realities. So minimum requirement of any mathematical model. On top of that, you can also require some other reasonable common sense properties. For instance, if you have a problem where energy, you expect it to dissipate, that indeed what you call the energy will decay, that velocity and acceleration will not become infinity because that doesn't make too much sense physically, and so on. Okay? So, as we will see, the Clay foundation problem about Navier-Stokes equation is concerned precisely with this issue of self-consistency, that is, existence of acceptable solutions and velocity remaining finite, and not with the accuracy of the model to reproduce reality. That's sort of not a mathematical problem, that's a scientific problem, but of a different nature. The mathematical problem is this internal consistency problem. Okay. So, so what is the physical phenomena that Navier-Stokes equation represents? Well, when I was thinking how to explain, I tried different type of models, and I was not satisfied with anyone. And finally, I thought that the correct version of the model was the gourmet one. And the gourmet one consists of the following. You take a bottle of olive oil with no air inside, so full. You put a little bit of oregano and red pepper as tracers. You shake the bottle really well, and then you sit it on the table. And the fluid is moving. And so what you want to do is you want to be able to reproduce how that fluid with that initial velocity will evolve into rest. Okay? So let me point out that this sort of experiment has many similarities with the throwing of the rock. Okay? In some sense, the initial shaking of the bottle corresponds to the swinging of the arm, where you are sort of giving the fluid some initial velocity. Okay? And the releasing of the stone corresponds to putting the bottle on top of a table and then let the thing evolve according to its own internal workings, its pressure, its friction, and so on. Okay? And also, both models have mathematical similarities, and these are the ones I want to stress. First, both models are the simplest most economic way on describing the phenomena under consideration. So Navier-Stokes equation is the simplest family of equations that you can, in some sense, create to try to describe a viscous flow. Also, both are reasonable under reasonable conditions. In other words, if the velocity increases too much, if you are looking at a model where the oil is engine oil and starts to burn and reaches very high temperatures and so on, then the model is not that good anymore. But what is more interesting, and I think I want really to stress this because I think this was the great achievement of the mechanicists of the last century, is that the idea in both, in the parabola model, what you take is sort of rates of change, right? Discrete rates of change, velocity at time 2 minus velocity at time 1, and then you take smaller and smaller and smaller rates of change and transform the average problem into an instantaneous, into a infinitesimal equation, right? Which is acceleration equal to minus constant downwards, okay? And here too, the great achievement of these people was to study these bulk quantities, these bulk average laws, reduce it to smaller and smaller physical domains and intervals of time, and that will allow them to transform these bulk laws in infinitesimal equations. And this is one of the threads I want to follow, okay? And both mainly, those equations, what they do is simply balance the acceleration with the forces, internal forces in the fluid. Or faster than any given particle, then the flow pulls that particle faster. And I'll try to later explain that idea a little bit more in detail. Okay? So before doing that, I want to take some time. So what I plan to do is I plan to discuss what each of the 4 terms here are: incompressibility, well, acceleration, more or less everybody knows, pressure, and the viscosity effect. But before doing that, I want to take some time, because I think it's important to understand why Navier-Stokes equation is difficult. I want to take some time in discussing the 2 ways which usually people in continuum mechanics record data. Okay? There are 2 different ways, and these are Lagrangian and Eulerian coordinates. Okay? And that's why I chose the oil with the oregano and the pepper, because it's, I think, really probably the best way to explain them. Okay? So in Lagrangian coordinates, you have the bottle, the fluid is moving, and you gather information from each individual particle moving on the flow. Okay? You have a particle of oregano, pepper, maybe a little drop of oil, and it's like if you were able to put in each little drop a set of sensors, right, and then receive the information that the particle is moving, the oregano is moving at such a speed, with such acceleration, with such density, and so on. Okay? So for instance, a data table in Lagrangian coordinates will be the following. I label the following particles, and then after 1 second, 2 seconds, 3 seconds, I say what the speed, or what is the acceleration, or what is whatever that particle is doing. Okay? In Eulerian coordinates, instead, what you do is you concentrate in every physical point inside the bottle. So you concentrate on each particle and register what is going through it. You know, if oregano goes by, and you never see it again. You keep looking at that point, and you just concentrate what happens there, and you record what the data is doing there. Another way of thinking on it is, suppose you have a crowded highway, right? And Lagrangian coordinates will be if each car is reporting to you, is giving information to you. While Eulerian coordinates is like a helicopter hovering over the highway and just looking what happens at this point and at this point. And the helicopter doesn't follow each particular car. Cars go by, right? He just records what is the speed of the car going through this point at this time. Okay? So, for instance, this will be the velocity field in Eulerian coordinates at a given time t0. You're looking at the space, and here you have this velocity, and so on. Okay? So in Eulerian coordinates, you only see a particle as it goes through a point. You never see it back. And so basically what the main quantity you record in Lagrangian coordinates is the position at time t of the particle that you label with some name at time 0. Okay, so your name is X, and you say that particle at time 0 I call X, right? I call whatever, now is in position Y. So Lagrangian coordinates, the main description of Lagrangian coordinates is by giving the position of every particle at every instant of time. Okay? Well, for the Eulerian observer, since he doesn't care about particles, the central information he has is just the velocity field that is going through any fixed point in space. Okay? So why do I take this the time to make this discussion? We'll see later is because in fluid mechanics both concepts in some sense mix. Okay, so let's keep this for a minute in the refrigerator. We will discuss it later. Let me now start to discuss the terms and the considerations. So the first statement in Navier-Stokes equation is that the fluid is incompressible. Okay, so we are all basically have an heuristic idea of what compressibility means. It means to just take in some substance or material and by pressing it, reduce its volume. Right? Gases are usually compressible. You have a bottle, you squeeze them, they can reduce the volume. Fluids are usually, under reasonable physical situations, uncompressible. There is no way you can reduce its volume. Okay? So this is the first statement of the equation. Now, what does it mean mathematically? Okay? So you can say what it means mathematically in Lagrangian coordinates or in Eulerian coordinates. In Lagrangian coordinates, it means that any little parcel of liquid or fluid you take, if you follow it through its life, it's going around and around and around and make the form, some may be very long, very stretched, and so on. Nevertheless, the volume is always the same. That's what incompressible means. Okay? In Eulerian coordinates, you cannot talk about the volume traveling around. You have to fix your attention in a piece of space. So in Eulerian coordinates, you just take any fixed region and you look at the flow entering and going out instantaneously in that region. Where you say, okay, here there is flow coming out. On the other side, there is flow going in. I average it all, whatever is in and whatever is out. I add it up. I have to get 0. Incompressible in fixed space means that whatever goes in has to go out somewhere else. Okay? Now, here I want to stress then this beautiful idea of continuum mechanics. This is something that I can apply to any little volume of space. Can apply to this area, to this area, to this area, to this tiny area. And it's it's additive, it superposes this property. Therefore, I should be able to express that by an infinitesimal relation. Okay? And the infinitesimal equation, I just put it here for you to see, in Lagrangian coordinates, simply says that the determinant of the differential of y with respect to x is 1, and in Eulerian coordinates that the divergence of the velocity field is 0. And it doesn't matter what it means, but what is important is this idea that you can, by applying the bulk property to smaller and smaller and smaller domains, rewrite that as a differential equation, as an infinitesimal relation. Okay? So much for incompressibility. I'll discuss a little bit later what is the meaning of that in terms of Navier-Stokes equation, but that's what incompressibility means. So acceleration, well, I think more or less all of us have an idea of what acceleration is, or if you speed on the highway, it's linear acceleration. You take a turn, you have centripetal acceleration. So basically, acceleration is just the instantaneous rate of change in the velocity of any given particle in the flow. In other words, you take a particle, measure its velocity at some time, measure its velocity a little bit later, make the infinitesimal quotient, take the limit. That is acceleration. Okay? Now, I want to stress a very important point about acceleration, that is that acceleration is a Lagrangian concept. In other words, to compute acceleration, you take a particle at a time, you look at it a little bit later and see what is the instantaneous rate of change. Okay? In Eulerian coordinates, to complete the Eulerian coordinates instead, the situation becomes much more problematic. And the reason is that the velocity field, when you try to compute acceleration in Eulerian coordinates, appears twice. Okay? Appears first because velocity is changing, but also appears because the formula for acceleration says that you have to compute the velocity of whoever is going through point X at time t0, but also you need to know the velocity of that same particle an instant afterwards. That's what acceleration says. It says look at the velocity of the particle now, look at the velocity a little bit later of the same particle, and see the instantaneous rate of change. But the fluid has taken that particle away from X. In Eulerian coordinates, you were looking at X, and the particle is not there anymore. The particle has drifted away due to the velocity field itself. So the particle is here, and an instant of time later, the particle has drifted away. And that means that when you try to write the formula for acceleration, the velocity appears in a non-linear fashion. Okay? When you do the increment, you have to consider the velocity not at x, but at the point where the particle has drifted by the velocity field itself. And that means that acceleration, which is so beautiful and simple quantity in Lagrangian coordinates, it becomes a non-linear quantity, complex non-linear quantity in Eulerian coordinates. Okay? And I think this is basically the course of fluid dynamics. The course of fluid dynamics is that you constantly match quantities which are natural in Lagrangian coordinates, like acceleration, with quantities like stress, which are sort of natural concepts in Eulerian coordinates, which are, you match dynamic concepts with the static concepts and so on. Okay? And that's why equations in fluid dynamics are so difficult, because you write them in a way, there is a piece that doesn't match. You write it the other part doesn't match. Okay? So let me go a little bit to the right-hand side. Okay? So the right-hand side says acceleration on the left says is due to the pressure gradient and the viscous effect. So let me discuss a little bit about pressure. Okay? I think that sort of, at least mathematically, pressure is a real bad guy in the Navier-Stokes equation. And the reason is that in incompressible flow, at the difference with compressible flow, with all the other mathematical phenomena, the interplay between pressure and velocity is instantaneous. There is no time lag. You have incompressible flow, you put pressure in one end, the pressure is instantaneously felt at the other end and without attenuation. Okay? If you have compressible flow, you put pressure here, it takes some while to get here. If you have the mathematical theory of heat, you heat up here, heat propagates instantaneously everywhere, but with a big decay. When it's far away, it has very little effect. That's not the case with pressure in incompressible flow. Pressure instantaneously, whatever modification in the velocity is far away, it's felt everywhere through the pressure and the other way around. So I think this is what makes out of pressure the real problematic terms. So mathematically, the acceleration due to pressure is simply proportional to minus the gradient of the pressure. In other words, if pressure is constant, then the fluid does not accelerate, at least not due to pressure. You increase pressure here, then the fluid accelerates, so the fluid is going at constant speed. You add pressure here, then the fluid accelerates towards the area of lower pressure. Okay? And again, this is something that you can first establish sort of in bulk properties and then get the infinitesimal relation. But I'll discuss later, try to discuss a little bit about pressure, but remember that sort of the pressure induced, for instance, by the fluid turning in a corner of the bottle instantaneously is felt all over the bottle. So it's a typical example of an incompressible thing is a train versus traffic flow. In traffic flow, there is a crash, the car coming behind slowly stop, maybe some can crash, but the fluid compresses. In a train, the train hits something, derails all of it, because it has no room to compress. Okay?
Is that what water does? I mean,
If you ever try to fix a pipe in your home, you'll realize how incompressible water is. You know. That's why hydraulic systems are so good for moving objects or lifting weights, because you put pressure in the fluid. In an hydraulic jug, you put pressure in the fluid, and the pressure is felt in. We can lift 10 tons, 100 tons, right? I mean, just with a little bit of pressure you add in the other end, okay, because of incompressibility. Okay. So this is pressure. I think, for instance, in Navier-Stokes, let me give you some sort of reason why I think that pressure can be the culprit on creating infinite speed in Navier-Stokes. And I think sort of a visual effect you can take. Suppose you take this table. I used to play with pennies when I was a kid in my home. Many of you did, right, with a bottle of pennies. You put pennies all over the table, and you pack them closely, so they are sort of incompressible, right? They're touching each other, right? And then I think that if you do that, and you squeeze the edge of the tables just right, you should be able to make the center of the pennies pop out, okay? And I think that's what could happen in Navier-Stokes, that the pressure from infinity can squeeze the flow just right to create a singularity inside. Okay? But now let me talk a little bit about viscosity, that is the good guy. Okay? So the other part of the Navier-Stokes equation establishes that the fluid is also accelerated by the drag that the surrounding fluid exerts on a given particle due to different speeds. Let me try to give you an heuristic idea of what happens. Okay? So suppose you have that the origin, at a given time, the particle at the origin has zero velocity. Okay? But the particles surrounding it are slightly moving to the right. Okay? Since the flow is viscous, that is, since there is friction between particles, then these particles moving slightly to the right will push the particle in the center, will try to accelerate the particle to the right. Okay? And so in that spirit, then, so if you want to sort of give a precise meaning to this idea of the particles dragging the flow, then what we should do is the following. You take a point, right? And you should take a tiny ball around the point, right? And you take in this tiny ball around the point, you take the average velocity and you subtract it from the velocity of the point, right? And that gives you exactly the direction in which the fluid is accelerating the particle. So the acceleration due to the viscosity effect, in some sense, should be proportional to this quantity. The average velocity around a point minus the velocity at the point itself. Okay? And since the pictures clearly indicate sort of that this is a quadratic effect, right? This is a quadratic effect on the velocity field. Since this is a quadratic effect on the velocity field, if you want to get a quantity that is not zero, you have to divide this by the radius of the ball square. In other words, you take the average in a tiny ball of the velocity, you subtract the velocity at the center, divide by the radius square, takes the limit, that gives you an infinitesimal quantity that reflects the drag that the surrounding fluid exerts in each particle. In fact, this is a very famous quantity. It's called the Laplacian. The Laplacian of the velocity is exactly the limit of the average velocity minus the velocity at the point divided by the square of the radius. Okay? Notice that this choice of a measure of the drag that the particles exert at the point is not, is not too justified. It's just a choice. You could say, no, the drag may depend on the speed. I mean, if the points are going very fast, maybe the drag is bigger or smaller. If the velocity is sort of rotating in some special way, maybe you know, the drag is different. So this is an ad hoc law, okay? And so one could argue that, well, maybe this is the reason why Navier-Stokes equations doesn't work so well, because when the fluid becomes, you know, at high speed, who knows what happens with the molecules, right? They burn. Why should they interact the same way at high speed that at low speed? Okay. Nevertheless, so this is the last term of the equation. Notice, let me point out that this is, in the vein of what I was discussing before, this is essentially an Eulerian concept. If you try to translate this to Lagrangian coordinates, it's a mess. That's why Navier-Stokes equation is usually written in Eulerian coordinates, because it's the least of two evils. The acceleration doesn't write so well, but at least the viscosity writes reasonably. The other way around, the viscosity becomes some very nasty expression. Okay? So basically, I think by now I have described, let me write for you, then the Navier-Stokes equation. The Navier-Stokes equation says that the flow is incompressible in the Eulerian coordinates, divergence of the velocity equal to 0, and that the acceleration, which in Eulerian coordinates we have to write as Vt plus Vdv, is proportional to minus the gradient of the pressure plus the Laplacian, that is the viscous effect of V. Okay? So what is the expectation at this point? You know, if we go back to the problem of the Battle of Hall, the expectation is that if you give me an initial velocity field, that if you tell me at time 0 what the velocity of each particle is, then I should be able to reconstruct the flow for all times. Okay? And so this is the option 1 of the problem. In other words, the problem has two possible solutions. Okay, and the Clay Foundation accepts for his money any of both solutions. So the first solution says, I give you a nice initial data, and you find for me a nice solution, a solution where velocity remains finite, acceleration remains finite, and so on, for all time. Okay? And as I said, this is a matter of internal coherence. It has nothing to do with the model reflecting reality. Okay? It has to do with the model being coherent. That is, that if you give me data, the equations at least have a nice solution, close to reality or not. Okay? Now, the other option that the Clay Foundation gives you is, okay, if you cannot do that, show us that the opposite is true. That you can find a solution, you give me a nice initial data, and you find a solution that starts very nice, and all of a sudden, at some time in finite time, it becomes infinite. Okay? Any problem with it? Okay, so these are the two options. Or you are able to solve the problem with a smooth solution for all times, or in finite time, the velocity becomes infinity somewhere. Okay? Now, what it is known up to now? Well, what is known is that some sort of weak solution exists for all time. This was the work of Jean Leray, who I had the honor to meet. He died recently. He's one of the great mathematicians of this century. So I also have his picture. He constructed in the 30s basically a theory that included, you know, he basically was one of the fathers of the theory and included the construction of weak solutions, to reasonable weak solutions to the Navier-Stokes equation. Okay? The second thing it is known is that if the initial data is nice, then these weak solutions for a while remain nice. In other words, the effect of the initial data lasts for a while. It's also known that after another longer period, due to the fact that energy dissipates, then the solution becomes small enough that it's forced to become nice again. Okay? If you think heuristically, the reason is that both pressure and the bad part of accelerations are quadratic functions of velocity. Now, if velocity is very small, the square of something small is much smaller. And so you can really prove that that's not bad for you, that you can control it. Okay? The problem is that in between, in the middle, in this period where the goodness of the initial data has disappeared, and still there has been no enough energy low, not enough dissipation to force the solution to be small. So there is this mid-range where you cannot prove that solutions remain smooth. In fact, you cannot even prove that the energy is the natural combination of energy, kinetic energy plus dissipated energy is preserved. You cannot even prove that. Okay? As it was mentioned before, we proved with Kohn and Nirenberg many years ago that in this unknown region, the set of points where the solution can become singular plus all its limiting points, that is, add to it all the judge you want, all the limiting points of the points where it comes, it cannot fill a curve in space-time. Whereas the Hausdorff one-dimensional measure of that set is 0, which heuristically means that. It means that if a singularity appears at a time, it will not persist in time, will disappear instantaneously. It cannot fill a curve in an instant of time, nor any combination. That is, in the 4 dimensions that space and time are, the singularities are unable to fill a curve. So if singularities exist, they are really a very minimal set, physically sort of irrelevant, because you will never see them. It will not have any effect. Sort of what is my personal belief? My personal belief, well, is the following, is that if indeed Clay option 1 is correct, that is that solutions remain always regular, this has to be attained because of a different approach. And sort of all the approach that had been taken with the Navier-Stokes equation up to now was to take ut minus Laplacian of u, which is a very good term. It's like the heat equation is the very fast dissipation term, because viscosity dissipates energy very fast, and put everything else on the right-hand side as treated as junk. Okay? And so if you do that, I mean, there are many reasons, scaling reasons, there are a bunch of reasons that tells you that basically this result is optimal, that you cannot go beyond that. Okay? So if you just look at the structure of the equation at that level, heat equation plus a quadratic equal to a quadratic term, you cannot go further than this. You have to understand, I think that you have to understand it in Lagrangian coordinates. I think that the way to understand Navier-Stokes equation, if indeed solutions are regular, is because there are some concepts like the fact that matter doesn't penetrate itself, which is not transparent in Eulerian coordinates. In Eulerian coordinates, you have the velocity field, and if you want to reconstruct the position of the points, you have to integrate the trajectory of its points. Okay? In Lagrangian coordinates, the points are there. If, on the other hand, Clay option 2 is correct, that is that indeed there are singularities, well, there is a traditional way of trying to find singularities with simple structure, that is to find solutions which are called self-similar focusing solutions. Self-similar focusing solutions are solutions which at different times basically have the same structure but shrunk. For instance, a cone, if you take a cone in space and time with the vertex at time equal to 0, that's a self-similar picture. At every time it's the same circle that is shrinking itself, and you can make a dilation that is sort of the same value in space and time, and you get the cone again. Okay? So there is a tradition of trying to find self-similar focusing solutions. These solutions such that the flow at every time looks sort of the same, squeezing and squeezing and squeezing, and at time equal to 0, a singularity will pop at the origin. People have tried that with what is called the Leray self-focusing, and it was proven by Nejas and Verac and someone else recently that that's not possible. So if you are going to find a singularity for Navier-Stokes, then I think you have to do a different scaling. You have to do an Eulerian scaling, that is a scaling that corresponds to the equation with no viscosity. And there is a way you can do that in such a way that the viscosity becomes a smaller order effect. And I think That's the only possibility I see in constructing a singularity for Navier-Stokes. So let me stop here. I'll be happy to answer.
Any questions? I have a question. I mean, the problem, the clay problem, is that in a bottle or is that in all space?
I think this is a shortcoming of the way the clay problem was set. I think it should have been set or in all of space. The clay problem is set in all space.
In all space.
But I think it's equally valid to solve the problem and equally hard to solve the problem in a bounded domain. You know, Navier-Stokes has a natural boundary condition, which is called the non-slip condition, that the flow adheres to the wall of the container. So velocity is zero on the wall. So I think the problem should have been set that to solve in all of space or in a bounded domain with non-slip boundary conditions. So, but the problem, the clay problem is in all of space. You need a lot of oil to solve the clay problem.
Which is harder? Is it the same? Which problem?
I think philosophically it's the same. If you find a way to solve one, you will find a way to solve the other. Yeah.
Other questions? Yeah.
So
Here.
there are two options. What
Yeah.
is your ETB feeling? Which would you prefer?
Well, you know, there is a very classical observation of Serring that if you take some vector field, a gradient of a harmonic function, some special vector field in X, some special velocity field, and you multiply it by your favorite function in time. Let me see if I have it. This is an observation of Serring that says take, for instance, 2x squared minus y squared minus c squared. This is a harmonic function. You take the gradient. So it's minus x, x minus y over 2 minus c over 2. So you take the gradient of any harmonic function, okay? And you multiply it by your favorite function of time. This is a solution of Navier-Stokes equation for all times, because everything is gradient of the pressure. Okay? So this is a solution of the Navier-Stokes equation, which is driven by pressure at infinity. You see, instantaneously the flow, the role of the g of t is like you are controlling the pressure at infinity. And you do with the fluid whatever you want. You know, you can do your g of t become infinite at some instant of time, which means that the fluid blows instantaneously everywhere, right? Now, you tell me, well, no, but I don't allow you that. I take initially data which is compact support. Well, pressure instantaneously travels to infinity. The pressure does not have decay. There is the pressure, if you start with a velocity perturbation in a small domain, the pressure has very slow decay at infinity. It does not have exponential decay at infinity. So the interplay of what is local and what is infinity is very strange. So where is the truth? If it's close to this, or if it is close to option 1, I think it will only be seen when the problem is solved.
Yes.
Louis, could you comment on compressible equations? They don't have this paradox, but they're still complicated.
It's a different type of singularity because compressible equation, for compressible equation, the velocity, the typical singularity is discontinuous velocity. In Navier-Stokes, if the velocity is bounded, the solution is infinity. So when you talk discontinuity for compressible and discontinuity for incompressible, we are talking about different things. Okay, it's, compressible discontinuity is a shock, it's discontinuous velocity, while Navier-Stokes is infinite velocity. Finite velocity for Navier-Stokes is infinity. Okay.
Yes?
What's known about there's a lower dimensional version or higher dimensional version of this problem?
Well, there is a two-dimensional version, which is flows which are planar. not that lie in a plane, but that in every slice look the same. This is a very classical result that in 2 dimensions, Navier-Stokes solutions to Navier-Stokes equations are always regular. So in 2D, Navier-Stokes is regular, and it's a classical result. You can also deduce it from our theorem, because if you have a singularity, it will fill a full line. Yeah.
What happens when viscosity is 0? Can you comment?
Okay, that's the Euler equation. When viscosity is 0, that is without viscosity, that's an equation which is earlier than Navier-Stokes, which is called Euler equation. Euler equation, as Charlie Pfefferman points out in his presentation, is sort of an important, to understand it in some sense, may be an important previous step, because it's a simpler structure, and you want to know if in that case you can produce singularities. In Euler equation, there are many solutions that indicate that the Euler equation is sort of much worse than Navier-Stokes, that doesn't have the regularizing effect of viscosity. But still, it would be very important to understand how infinite velocity can appear in 3-dimensional Euler, and see if that gives you a guide. In fact, that's what I think it should be done, to find a self-focusing solution for Euler, and then from there, sort of perturb it to Navier-Stokes.
But there is no money for it.
There is no money.
All right. Maybe it's time to think about refreshments. I remind you, 2 weeks from tonight, we'll have the 6th lecture by Dan Fried on the Hodge conjecture. So the food is, as usual, any newcomers down to the left. Thank you.